Next speaker is Pierpaolo Sorrentino. He's from Université Aix-Marseille, and he will be talking about brain dynamics, so how the structural connectome shapes fast transients. Pierpaolo.
Hi, everyone. So basically, my presentation will be slightly different than what I've seen so far. Basically, what we normally work with resting state, and we wish to investigate whether some principles drive the unfolding of the activity over time at rest. So basically, in reality, the idea behind it, or the question, or the fact that we want to explain, is kind of evident, and is this: imagine you have a person which is just resting. If I basically start reading a poetry to this person, or ask to make some complicated calculation, this person can do it if he already knew how. Quickly, he can start doing it. At the same time, if I throw a stone at this person, so a completely different kind of stimulus, this person would probably dodge it or try to dodge it. So it would somehow put in place very complex behavior very quickly, adapting to very different kind of stimuli. This is, to do that just in a very hand-wavy manner, you have two conflicting demands. Because on the one hand, you want communication to be efficient. You want the coordination, broadly speaking, to be correct and reliable. You want messages to pass without mistakes from A to B. On the other hand, though, because you want to be able to be responsive to different set of stimuli, you also want this system to reconfigure very quickly. So, for instance, if you look at the top right part, you have a system in which you imagine these are nodes, so elements, and time flows from left to right. If I stimulate a little bit this system, there is runaway excitation and all the system gets activated. However, if I stimulate the system here, I give a very strong stimulus and the activation quickly dies out. And these two features are not what seems to be desirable as to explain what we see. So such capability of reaction and of adaptation to different stimuli. There are certain physical systems where basically you can have that given a certain stimulus, the activity propagates in time, but does not spread too much, meaning that a pattern forms, a pattern of activation forms, which can be very different according to the initial stimulus, and perhaps can be used to store information. Of course, many very smart people worked on this, and they noticed that physical systems, like an operational regime which is near a phase transition or second order phase transition, seems to display these kind of desirable features, but this is not what I will talk about. It's not what we're interested in. To investigate this, we used MEG, which I won't introduce because it has been done extensively. I introduced our particular one, and in Naples at Partenopea University and the National Research Council. So this is the MEG. This is the subject with the head inside, and this is the squid array, which normally you don't see because it's inside the dewar. And this can, as it was said, record the activity produced by the brain. We can source reconstruct. I will absolutely skip all this because it's has been already extensively been explained. I try to run this movie, which is just, I slowed down 1 second of activity because I want you to have like a visual intuition of what we're talking about when we say that the activity is fast and is reconfiguring over time. Let me know if you can see it. If you can't, I will just stop it and go ahead. So I hope the...
Yes, we do. Yes.
Oh, that is great. I was not even hoping. Okay, so basically this is only 1 second of activation, of source reconstructed activation. A few steps have been made to make it a bit nicer, but the information that you see is there. You see this burst of activity that vary in size and vary in duration. And while they're obviously complex in the layman acception of this word, they are complicated. On the other hand, they also don't seem noise. Like there is obviously some structure to them. Then how to try to unfold such a complicated thing and to get some information from this dynamic, which can be relevant, for instance, for clinical purpose, or at least to understand the principles beyond such complicated activity. So to start with, we borrow a very a technique from statistical mechanics, which are called neuronal avalanches, or avalanches more in general. So this is a concept or a framework where basically you try to characterize the unfolding, the spatiotemporal unfolding of activations. Again, for the purpose of this talk, we can simply think of avalanches as a spatiotemporal fluctuation. So naively, we say that we have our source reconstructed time series, we z-score them, and then we threshold them, right? At each time point, we consider as active a region which has a z-score above the threshold, say 3, and we consider inactive a region which is below threshold. So when we do that, from the time series such as these, we obtain a raster plot where you have time on the x-axis and thresholded activity on the y-axis, such that, for instance, this region was not active, is always equal to 0, it's below threshold, and then suddenly it goes above threshold and you get a burst of activity. I want you just 1 second to pause and ponder on one weird thing that we're doing here. We are literally saying, with such a z-score, 95% of my signal, I don't care. I will focus on this very tiny bit. You can even go higher with the threshold and very few things changes. All right. Then, in this case, this would be one avalanche. As I said, this would be another avalanche, this would be another avalanche, and so on. Now, they can have plenty of shapes, and how do we make sense of this? At the end of the day, as I said, we're interested in knowing how flexible the system is. We want to try and find a measure of how quickly the system changes configuration, even when, of course, it's not being explicitly stimulated by a task, because this is resting state, remember. So again, we now magnify one of the avalanches. This is, of course, like a toy cartoon, just to try to convey the technique itself. So you have one region gets activated in time, then more region gets activated, then more region gets activated, and then the avalanches fades out. I say here time bins because we bin the time series such as to have a branching ratio equals to 1. But again, this is not a fundamental detail to the purpose of this talk. Once we have our avalanches, we see the spatiotemporal unfolding of this perturbation, let's say, of this activity that starts over here to be particularly high as compared to whatever this region was doing. And basically, we see that we construct an avalanche pattern, which is defined as any region that was active at any moment during the avalanches. So for instance, this region over here was never active at any time, and henceforth, it does not belong to the avalanche pattern. However, this region was active at some point, and so it's part of the avalanche pattern, which is specific to this one avalanche. This region as well was active, and then it's part of the pattern. So at this point, we have a collapsed version of the avalanches, which is a very short burst of activity. We're talking here about 20 milliseconds, 10 milliseconds, up to 300, 400 milliseconds, but they're fast as compared to other techniques resolution, although span across scales as well. We basically then have this short representation, collapsing time, and basically just having the spatial spreading. And we can now count how many unique patterns occurred in a certain time. And this set of patterns we defined as a functional repertoire. So the configuration that the system does explore in time, in time, and we consider this as a proxy for the flexibility of the capability of accommodating potentially different stimuli quickly and effectively by the system. Just to quickly tell you, the avalanches also have certain properties, such as the distribution of the size or the shape collapse. I will tell you in 1 second what this is, which are in accordance with some prediction made from mean field theory. So that's why so many people worked on them and think that they may be a way to look at some deeper structure. But whether this is the case or not is still debated and is not relevant for what I'm going to talk about. Just one interesting, what is the shape of an avalanche? The shape of an avalanche, as I said to you earlier, say you have one region active, then you have in this, let's make a toy smaller avalanche, 3 region active and 1 region active, just a toy. Then the shape would be 1, 3, 1, right? So it's a kind of the profile of how many regions are active in time throughout the avalanche. And despite the fact that the avalanches range in duration across scales, so they can be very short or long, much longer, you only have one single exponent to fit the shape of the avalanche to a unitary duration. All this to say that there is very nice statistical property that we should exploit. To test whether our metrics or our estimation of the functional repertoire can be of use, we tested it first on Parkinson's disease. So this is a basal ganglia disease, which is normally considered as motor, but really the symptoms are widespread between motor, cognitive, and other domains as well. And we selected 39 patients and 38, so Parkinson's disease patients, and 38 matched control by age, gender, level of instruction, and other parameters. And they underwent a resting state, eyes closed, acquisition in the MEG. And we, simple as that, measured the size of the functional repertoire in these 2 groups, which is nothing else than counting how many different avalanche patterns occurred. And we see that this number is reduced in Parkinson's disease, such as the dynamic would appear to be somewhat more stereotyped as compared to controls. However, 2 possible explanations are there. On one hand, we can perhaps believe what I just said and say, oh, right, then it means that indeed the activity is more constrained. But one can also think, well, I think really that Parkinsonians are just slower, but if you give them enough time, they would have explored the same space, the same state space. Of course, we can't check that, needless to say, but we can have a proxy or at least a hint of whether this is the case or not. So we counted what is the switch rate. The switch rate, it's simply per each subject, how many times a region went from 0 to 1, so from non-active to active, or from active to non-active. That's it. So how many times there is the regions switch. And what's interesting is that in Parkinsonians, apparently, the number of switches is higher, which was really quite a surprise, meaning that the system does switch between configuration. There is a lot of switching, but the combination that actually happened to occur, the set of combinations that happen to occur is reduced. This is some further checks, which I won't go into. And what's interesting is that the number of states So the size of the functional repertoire seems to have some inverse relationship with the UPDRS, which is a clinical scale, which is kind of nice because you think you can imagine or have a hint that perhaps it is true that if the system restrains its flexibility, restrains its capability of exploring its state space, then the patient is worse off. And although this is a very tricky data, so one has to be very careful, but we wanted to know whether certain regions are more involved than others in configuration that are pathological, so to say. So to do this, we took all the configuration of everyone, patients and controls, and we split them into two. Not, as you might think, patients versus controls, but rather configurations that are in both versus configurations that are in either. So the configurations that are in either are the ones that happen in one group or the other group, but not in both. They're somehow the ones that distinguish the two groups. And we ask, is there some regions that always happen to be there in the patterns that distinguish as compared to the patterns that they have in common? So they're not probably as relevant to what we are concerned now, which is different with PD. And we see that the regions that happen to be different in the two groups are the basal ganglia. Of course, one has to be very careful. Source reconstruction problems, deep sources, people that are much more experts than me in this talked a lot about it. Nonetheless, at the level of a difference between two groups that should be otherwise comparable, this appears to be the case. And this was completely uninformed. And it's relevant, it seems to be relevant from a neurological perspective because the basal ganglia happen to be the ones that we know are mostly involved in Parkinson's disease. Then we asked what is the mechanism that allows or does not allow such reconfiguration? And we imagine, well, we did not imagine, but there is a lot of work made by many people showing that if a system is if a region depends too much on what everyone else is doing, the system will not be flexible. It will have a stereotype activity which is somewhat similar among regions. The prototypical idea is in epileptic seizures, of course. So we basically try to link the size of the functional repertoire with the average synchronization in the beta band, which shows beta band for, well, neurophysiological reasons related to PD, because we know beta band is important over there, and we need to make a band to estimate synchronization. So we basically checked, and we see that actually the shrinkage of the functional repertoire also inversely relates with synchronization as estimated with the phase linearity measurement, which is a synchronization measurement similar to PLI or ELV in terms of interpretation, just a bit more resilient to noise. So this is nice because it somehow shows that perhaps this could be a general mechanism. We already knew from a previous work that in a different disease, so amyotrophic lateral sclerosis, something in this line happens. Now what we're trying to do is we're trying to move away from PD and see whether a certain relationship between a change in the dynamics holds for various, very different in nature disruption of the network. So in amyotrophic lateral sclerosis, we have showed that the topology of synchronization is way more connected in advanced patients, so patients that are very, very advanced in the disease, near the end of the natural story of the disease, and then early stage, and they're much more similar to controls in that the topology is not as compact. Then I was very curious to know, right, in the advanced stage, which is now here, apologies for that, we already know they are hypersynchronized, the topology is hypersynchronized on average. But does this also relate to the fact that the dynamic becomes more constrained? And you see that it appears to be the case even here. So the size of the functional repertoire that you see here in the advanced case shrinks as much as the topology becomes more compact. This was nice. And then, finally, we basically decided, we then wanted to investigate. At this point, as I said, we give away a lot of the signal. We focus on this very fast burst of activity, neuronal avalanches, if you wish. If you are from dynamical system, you can think of them as fast transients of activity in the flow of the system. It does not matter to me as much, but what matters is what makes them what they are, what makes them look what they are. So to do this, we focus on the neuronal avalanches, and we basically try to estimate the probability that if a region is active, so if a certain region is part of the avalanche, what is the probability that another region will be recruited by that avalanche at the next time step? So in this case, I have a region I is active 3 times, and at the following time step, region J is active twice. So the probability for this particular avalanche would be 2/3. Because twice J follows the activation of I. When you do that and you average across avalanches, so notice that in this case, there is no average across time. You're basically keeping the resolution of the device as it is. You don't average across time, but you average in space, basically. Because you have a specific transition matrix and you sort of average all of them for each subject. And you retrieve something that is resemblant of the structural matrix. So of the pattern of how the activity spreads, of how the white bundles traits link the gray matter bits structurally. So perhaps we can think that when a perturbation is generated locally, so an avalanche starts basically, then the activity spreads across the brain, but the spreading is heavily biased by the structural traits that are present. If this is true, this is relevant because we can then perhaps understand what happens when a lesion hits the system in a given point. And I'm concluding. Apologies for having been a bit too long. Just thanking Leo Gallo, which helped me a lot, the Naples MEG team, Victor Girsa, my boss, and Michael Braxby, Andrew Zaleski, which all contributed to the work. Thank you very much for your attention.
I was going to take minutes if you wanted, but
I can't hear you very well.
But you're
sorry.
Can you hear me now?
Yeah.
Okay, good. Sorry, I was going to tell you have a few more minutes, actually. I kind of showed up. I don't know if this made you go faster at the end of your talk.
Oh, it did a bit, not. But it doesn't really matter at this point.
I did, yeah.
I saw you there, and
yeah. So sorry for this. Okay, thank you very much. Thank you very much. Very, very interesting presentation. Are there questions from the audience? Let me see. I must confess, this was, as you mentioned at the beginning of your presentation, this was a bit farther from, at least from my usual average, field in some sense. So I will have questions, but they would seem very naive, probably. Let's see if
allow me to doubt.
No. Let's see if there are questions. Not yet, apparently. So no. Well, my first question is. So there's Giovanni Pellegrino. you want to ask it yourself? You can unmute yourself, I think now. Probably. Otherwise, I can do it. So Giovanni is asking, what tools? Okay, what tools do you use for this? I think you mentioned MEG.
Yeah, so all the analysis I talked about are made with MEG. Basically most of the processing is done with field trip. Normally what you do, you pre-process the signal using PCA to remove the reference, so to remove the activity of reference sensors, and then you followed by ICA, supervised ICA, to remove physiological artifacts. Then follow that, you have a clean signal, and we use the linearly constrained beamformer based on the native resonance of each participant to source reconstruct. The first bit was done using the AAL Atlas. The part in which I showed the correlation with the DTI was made both with the AAL and the DKT. So we used to make sure that the parcellation to some extent does not fully, at least trivially, justify the results. And then the rest, so the branching ratio, connectivity, avalanche estimation, and blah, 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 it's all code that I wrote, basically. So in-house.
Yeah. I think Giovanni was mainly referring to the tool. So I think it was, well, what tools? No. Yeah, you probably gave the right complete answer. Also, Giovanni is saying thanks and wonderful talk. It's on the chat.
Thank you very much. Thanks.
There are two more questions, at least. One is from Gabriele Arnulfo. He says, can you please go back one slide and comment about the results for avalanche transitions and structural connectome?
Sure. Basically my, so these results come basically from the work that I do now, which I didn't show, which is try to make models of the brain activity. And to do that, which I do in a groups of people that, they do this, have been doing this for a long time, you want to know what are the features from the system, what is the best framework to somehow conceptualize the unfolding of the activity. That is my understanding and my position to this. So classically, even I have been working on synchrony for a very long time, normalized by age. And then basically I was very surprised to see that when you discard most of the signal, which is what you, what contains the periodic part of the activity, you still manage to retrace the structural connections. So to me, this is highly relevant because it's perhaps telling you that part of the coordination of activity which happens on the large scale is not necessarily mediated by periodic repetition, which are most likely part of it, of course, but part of it will also be due to long-tailed activity, so rare events that you inherently do not expect from a periodic signal, and that still are shaped up as the structures that are derived from different techniques. So in some sense, I find it hard to think of a tautology there because the two data are independent until they meet. And so to me, my understanding or my imagination is that you have a certain perturbation that for whatever reason is generated by the local circuitry. And then once this occurs, this perturbation spreads as it has to, but it spreads way more when the traits where the cables are, in some sense. And because the cables have a very non-trivial topology, which is scale-free, which is small word, which has mega complicated non-trivial features, this will reflect itself in the unfolding of the activity. And I mean, this has to be, this is just a correlation, of course, but it could be tested whether this is the case. Why, when you average over time and you find the activity averaged over time, you retrace the properties of the structure, which was shown multiple times earlier. So perhaps this is a way to conceptualize, to frame, because once you have a framework such as the propagation of perturbations, if this is the case, then you gain the possibility of using a very well-built mathematical machinery to describe the system.
Okay, thank you.
It answers.
Yeah, I was wondering also if you actually correlated the structural matrix and the transition matrix themselves, and how that and that across, I know, maybe frequency, or there are more brain regions that are more prone to being constrained by the structure to actually like propagate activity. I mean, because you have these two matrices, and all that you mentioned here, it's actually makes sense, and it's really great result. I was wondering if you actually quantitatively quantified actually what is the correlation between the structural matrix and the transition matrix themselves.
Well, so this was the slides that I kept. So at the group level, say for the AAL, the correlation is around 0.4 and 0.35, depends a bit of the parameter you choose to estimate the avalanches. And this is the individual correlation, so for each subject. And this is the average over 47 subjects. And this is what they look like. This is, I think, something like 4,000 points. And the correlation looks like this. This is what you obtain when you shuffle the data. I cannot go into the details. There are different ways of shuffling them, but the time is constrained. But this is a very hard, so to say, null that shuffles the avalanches only in time. So you keep the spatial structure, but you disrupt the temporal structure, and you still don't manage to get the correlation, which is as the one you observed in the data. You can also do models, which I did not show, in which if you couple the regions according to the structural connectomes, then you do retrieve that. And if you don't, as expected, you don't. But this is done in the dynamics, well, with equations that are otherwise complicated, nonlinear, and somehow replicate the dynamic of the system. For the regions, not yet. We have not done a region-specific analysis. In my opinion, I strongly expect from what I've seen that a lot of topological features will be a consequence of this fact, or can be interpreted as a consequence of this fact. So, for instance, regions that are more central, I expect them to be more to also be more central. I mean, topologically, in terms of structural topology, will also be more central in how the activity spreads, because the probability is more likely that a certain perturbation or signal or impulse, or according to the model, whatever, passes through it. So that's my understanding. Also, do note that there is a lot of noise that affects differently DTI and MEG. So one has to be very careful. I tried to do my best to really prove that something is there, but one has to be careful because the DTI is biased by some problems that can happen, and the MEG is biased by some other problems that happen, but they're not the same problems, at least. So in some sense, this is reassuring. Yeah.
Thank you very much.
Thank you for your questions.
Thank you, Pierpaolo. There are actually two more questions, but as we kind of need the main room also for testing the next connection, I would ask you to move, ask you and everyone who's interested, I would be interested myself, but to move to a breakout room. There's, if you go to breakout rooms, there's like room 9, which is a place where you can continue the discussion.
I will try to find it. I will manage.
It's just and just join there, and also for Roberto Guidotti and Chris Caritevlis, if you want to go there and ask Pierpaolo the questions, that would be wonderful, and everyone else who likes to hear the answer. And just so, thank you very much again, Pierpaolo. Beautiful presentation and very interesting results indeed.
Thank you.
Thank you.
Thanks. I
just wanted to mention two little things. One is that I found out that online events have this further disadvantage that you cannot claim, look, I am in Rome for 1 week, so I cannot teach. So this implies that I'm going to have to teach the next hour, so I won't be here. And I think Alessandro will be chairing the next hour. The second thing is I just wanted to recall that we will have posters in the lunch break, during lunch break. And these will be in the breakout rooms. So if you go to breakout rooms, you already see they have been prepared with the names of the poster presenters. So if you are interested in looking at the posters, you can just go there. During the lunch break, there will be a sort of slideshow with all the posters information. So you can see the authors and the content of the posters as a background image in the main room. And so you can decide whether to go and talk to the presenters. I think that's it. I see Pierpaolo still in the main room.
Okay, I'll meet you there then.
No, I didn't want to push you. Sorry. Thank you again. Yeah, I'm done. And so I'll be back personally, I'll be back at 2:30, but there will be Ale sharing in a few minutes. See you later.